In this video, I want to tell you about the proof that was stated in the lecture that path connectivity implies connectivity. This is a nice application of connectivity and curves and a lot of the tools. And it's a useful thing to develop intuition besides being a classical statement. And remember that a corollary of this fact is that convex sets are connected. And the reason for that is that in the convex sets, if you have x and y and c, then you can always construct a curve 0, 1 into c. So the gamma of t is equal to t times x plus 1 times t minus y. So the convex combination, and this is continuous since it's linear. It's quite direct to show. Every component is linear, linear functions are continuous, so components are continuous. And if your component y is continuous, then your whole thing is continuous. Okay, so we want to, there are many sets that are convex, and this is particularly important. So we want to prove that a path connected space is connected. Now, how do you understand this proof? How to understand this, what's happening? You have your space X, and it's path connected, so every point can be connected by a curve. And let's suppose we have our hypothetical decomposition into U and V that would have non-trivial intersection and be non-empty in this case. Now the problem is that this whole curve, if we restrict attention to that, it would have to cross the boundary somewhere. But there is no boundary because these are both open and closed, so that leads to either a contradiction, or you could try to think that actually what this picture has to look like is that this point lies in one of the sets. But then by connectivity of that curve, that entire curve has to lie in there. But then you can sort of start to increase this set to include everything by spanning other curves. So that's another way of thinking about this argument. Okay, so let's do the proof. There are a few steps. So there's a setup step. We connect by a curve, so we apply the definition. We cover the curve, or we go back to the pre-image, and then we derive a contradiction. Okay, so let's suppose we were in this setting. So this time we were going to do this by contradiction. Suppose we had this setting that we have these two sets, U and V, and we have a point X in U and a point Y in V. So we set that up. So set X be in U, Y is in V. Then because we're assuming that they're non-empty. Now by path connectivity, there exists a curve that connects these pairs of points. So let's draw that into our picture here. This is our gamma. Now, we want to say that this is a contradiction somehow, so by finding a point that has to belong to both. Well, let's look at the pre-images under gamma. Now, by gamma, since gamma is continuous, then we know that the pre-images are continuous. So since gamma is continuous, and these are defined as pre-images, then these are open by a theorem. But they also have two additional properties. They're non-empty. Well, why is that? Well, gamma A is mapped to X, and X is in U, so A is in U prime. B is mapped to Y, and Y is in B, so B is in B prime. They're not disjoint. They're disjoint because if you had a point that lied in both, then gamma of Y would be in U and gamma of Y would be in B. But we assume that U and V are disjoint, and that's so this cannot be. This cannot be the case. So the only way to resolve this is that actually U prime intersect B prime is empty. So we have disjoint, non-empty, open sets that cover A, B, but that is not possible. We should also say open, we should add this property that 0AB is contained in E cubed V prime. And I'll just say to check this. And the idea is that, well, V and U cover X, and gamma, it has values in X, so that every value has to be either contained in U or in V. But since AB is connected, there is no such decomposition into two open sets that are disjoint and open and non-empty, because it's connected. So that's a contradiction. In fact, they have to have a common point, and you could also contradict them too.